If resistors in series slow down current, what do capacitors in series do? Do they store more charge? Do they store less charge? And what happens if you combine a 2 microfarad capacitor and a 6 microfarad capacitor? Let's make these capacitor combinations very intuitive and how to solve them. Here's a quick refresher on what a capacitor is. It's 2 metal plates that store charge by building up electric fields, and it's defined as Q equals CV, with this being charge, this being capacitance, and this being voltage. This and every other formula that we'll use for problem solving today is on free cheat sheet in the description. And charge cannot flow through a capacitor. It accumulates on the plates. Here's the core idea of capacitor combinations. So let me draw something for you. What does this mean? These are your capacitors. All of the left plates connect to A, all of the right plates connect to B. What this means physically is that all capacitors will experience the same voltage coming in from our battery down here, and each one stores its own amount of charge. And since charge is given with this formula, then Q1 equals C1V, Q2 equals C2V, Q3 equals C3V. The total charge from the battery is the sum of all of these. So Q1, 2, 3, which leads directly into this formula. The equivalent capacitor, if you remember equivalent resistors, is kind of like that, equals C1 plus C2 plus C3. So this would be your single equivalent capacitor that will hold the same amount of charge Q at the same voltage V. This is how you would find it. Let's move on to another diagram that I'll explain. Here we have our battery and 3 capacitors that are connected end to end. This is what's happening here. Positive charge coming from the battery builds up on the left plate of C1. This draws negative charge onto the right plate of C1, which then touches the left plate of C2. This pulls positive charge onto the right plate of C2, which then touches the left plate of C3, and finally negative charge lands on the rightmost plate of C3. What this means physically is that all capacitors have the same charge. The voltage, however, divides into V1, V2, V3 through these capacitors, with each voltage being related to its capacitance with this formula taken from Q equals CV. We just rearranged for voltage. The total result for a single equivalent capacitor is given with this calculation. It's just like equivalent resistors. So the same charge is being pushed through all plates, like squeezing your current through a narrow pipe. If there's more separation, then there's a lower total capacitance. So that's how it works in series compared to parallel. Here's the intuition tip. If it's parallel, it's the same voltage and you add the capacitance, like in the first example. If it's series, like the one that we just looked at, it's the same charge and a reciprocal C. This is the reverse of how resistors behave. Let's go through an example problem to make some sense of the stuff that I just told you. C2 and C3 are connected in parallel, and they're both directly connected across this A to B line. This combination of C2 and C3 are connected in series with C1. So step 1, let's combine C2 and C3. So C23 is equal to C2 plus C3. That's the equivalent capacitor, which can represent this entire part by itself. So now a new capacitor, C23. Now we've simplified the diagram, and we can treat it like 2 capacitors that are simply in series. And the formula for that, find an equivalent capacitor to replace these 2, is like this, which is what we were looking at earlier. And then once you find this, you can replace these 2 capacitors. And then you can treat the entire diagram like 1 capacitor if you only care about total charge and voltage. So this is the core skill with capacitors, taking the mess, cleaning it up using rules like parallel adding and series using reciprocals. And then you go ahead and solve Q equals CV from the cleaned up version.